Hello, friends. I'm extremely excited to start another series on writing better code. This series will be all about design principles. Every developer should strive to enhance their code quality, right? Which brings us to a few common questions. How can we write high quality code that scales effectively, can be maintained easily, saves time, and adapts to change more seamlessly? Of course, object oriented programming language is a powerful tool in this regard. But is it enough on its own? Are there specific rules we should follow to ensure better object oriented programming? You might have heard about solid principles, but what exactly are they and what problems do they solve? Welcome to this comprehensive series on software design principles where I will answer all these questions. Here's what you can expect from this series. I have created a dedicated and detailed video on each design principle. We will discuss about how can you identify the design principle violations in your code. We will learn all this with simple refactoring of code samples. We will delve deep into understanding what Solid is and explore the problems it aims to solve. My goal is to inspire you to appreciate solid principles, guiding you towards writing more solid code in the future. A basic familiarity with any object oriented programming language should be enough to follow along with this series. By the end of it, you will have a comprehensive understanding of what solid design principles are and how to apply them, creating systems that are not only robust but also easy to change and maintained over time. But before we jump in, if you haven't yet subscribed the channel, please consider doing so to stay updated on all future videos about C Sharp and other technologies. So, with this, let's get started. Let's start by addressing the question, what are solid design principles? Solid design principles set the foundation for writing clean and maintainable software that's easy to understand. Now, what exactly do you mean by maintainable software? Let's say you have a class containing some common code. If your class is maintainable, you should be able to easily adjust this code to fit different needs. This means that if the current code structure doesn't solve the current problem, you can modify it without causing issues for other parts of the software. Of course, maintainable code is not only just to understand and debug, but also should be flexible. In simple terms, if you can easily tweak or expand your code, then it's considered maintainable. I hope this gives you a little better understanding of maintainable code. Don't worry, we will provide plenty of examples in our upcoming videos to make things clearer. Now let's address another question. Why is it important to write maintainable code? It's because unmaintainable code can slow us down in the long run. Confused by this statement? How does it slow us down? Let's imagine a scenario where we are writing unmaintainable code. Imagine you have multiple features to develop. Now, if you don't focus on writing good and maintainable code, you might be able to deliver those features quickly initially. However, as time goes on, adding new features or fixing bugs will become increasingly time consuming because reading messy code takes time. If your functionality works with messy code, please be prepared. It will slow you down sooner or later. And the worst part is, you might not even realize that your delivery is slow because of the mess that you or your team has already created. Now, let's see another reason for writing maintainable code. Often, we do not have complete requirements upfront, right? And now, with the rise of agile practices, changing requirements has become a new norm. Now, if our code isn't written properly, adapting to new requirements become a very challenging task. It will definitely consume a huge amount of time both in understanding the messy code and figuring out where to add new code. Of course, there are many other reasons for writing maintainable code, but I hope it's now a bit clearer how much value maintainable code adds to your software in the long run. And this is where our solid design principles comes in, helping us write proper code so that as and when requirement changes, it's easy to adapt our code to our changing needs. Okay, we have reasoned enough about why we need to use solid design principles. But this raises another question. We praise object oriented programming quite a bit, right? Why can't object oriented programming alone ensure we write maintainable code? Let's delve into this interesting topic. No doubt, object oriented programming offers numerous benefits, such as modularity through classes, enabling easier troubleshooting, reusability via inheritance, flexibility through polymorphism, and other powerful concepts like encapsulation and abstraction. However, it's also clear that object-oriented design can many a times be very poorly written, resulting in overly large classes and methods attempting to do too much, like saving customer details, validating customers, and exporting customer details all in one class. A web of dependencies, as seen here, where the class relies directly on numerous services such as data access, validation, export, etc., leading to tightly coupled code that's hard to maintain, scale, and test, affecting maintainability, scalability, and testing of the software. This is precisely where solid principles come into play, offering developers clear guidance on crafting high quality software that's maintainable, scalable, and testable. So, to summarize the benefits of solid principles, your code becomes easier to maintain and understand. Changes are quicker to implement, easier to adapt with minimal risk. Over time, the code remains highly maintainable. We will revisit this discussion to tackle specific software challenges these principles address in just a moment. But first, let's break down what SOLID stands for. So, S stands for Single Responsibility Principle or SRP, O stands for Open Close Principle or OCP, L stands for List Scope Substitution Principle or LSP, I stands for Interface Segregation Principle or ISP, and finally D for Dependency Inversion Principle. In our upcoming videos, we will deep dive into each of solid principles, discussing more on how they guide us to write clean and maintainable code. But before we delve into these principles individually, let's tackle an interesting question. How can you recognize bad code? What are the indicators of bad code? What are design smells that solid design principles aim to address? Let's begin this by exploring another fascinating question, identifying and understanding code fragility, one of the design smells that Solid tries to eliminate. So, what exactly is fragile code? To understand this concept, imagine we are looking at a few classes within an application. Suppose this is one of the class. Your application suffers from fragile code if making a minor adjustment in one area inadvertently breaks other unrelated areas, leading to unexpected and confusing errors. Certainly, none of us wants to work with software that breaks in unrelated areas at the slightest touch, right? Let's visualize this with a sample code in Visual Studio. So this is a product processor class. Now it calls isDataValid, where based on certain pre-processing logic, the isValid local variable is assigned either true or false. For now, I'm assuming it as true. Let me run this. Perfect. So our code works fine. Now let's say a customer has reported a bug and a very smart developer has been assigned to fix it. He debugged a little and figured out that the problem lies in the validation logic. So he made some changes there. And due to these changes, a new value got assigned to isValid local variable. Now let's assume the new value is false. Note that he only made changes in the validation logic. Now he updates the unit test accordingly and everything works okay. Now let's run the application and see. Boom! It throws an exception. Looking at the error, which talks about having an issue in the catalog reader's read product catalog method, he has completely no clue what has happened to the system. He just made a small change in the validation logic and he doesn't even change anything in the catalog reader module. So that's a fragile system. You made a change in one component and it broke some other unrelated component. Right now, it is in one place, but it could have been broken in many places. So, to summarize, your software would be fragile if a small change in one class or module creates new bug in other areas. Sometimes the bug has no conceptual relationships with the currently changed area. The primary reason for fragile code could be poorly designed relationship of the classes and tight coupling. Let's see our next design smell. That's the code rigidity. Your code is rigid if you can't change a piece of code without changing the other modules which are irrelevant and have no relationship to the code you try to change. Rigidity is the characteristics which makes the code difficult to change, where a small change in one part of the code leads to cascading changes in other parts. Let me explain this with an example. Let's say you have to fix an issue in your email module code base. You have estimated 1 day for this because you kind of know the fix. And while doing that change, you realize that you have to receive a new parameter in your send email method. You did it happily. But guess what? Then you realize that your change needs to be adapted in payment module as well. Okay? So you make the change, but then you observe that there are other modules which also need to be adapted. Now you have gone mad. Making all these changes, updating corresponding unit test took you a hell lot of time. And finally you say the issue was very complicated. But you know what? It was complicated because you have made your components very rigid. In the business terms, we can say a software is rigid if the cost of making a single change is very high. The main reason of rigidity is the high coupling between your classes. When the classes are tightly coupled, then it is very difficult to introduce any change easily. We will see how to take care of rigidity in our upcoming videos. Let's move to next design smell. Code immobility. Immobility is the characteristics of a software where the design is hard to reuse. Basically, the design might be so much coupled that it is impossible to take out something and reuse. Or maybe we can reuse, but the effort and risk of separating it from the original code is too high. Now, to overcome this design smell, you have to decouple your software properly. We will look into such code as well in upcoming video. Let's move to our final design smell, needless complexity. This is the characteristics of software where we design our software with too much anticipation of future needs, which is also known as over engineering. You must have heard about it. Basically, in the name of future extensibility, we tend to do over engineering, which often adds a layer of additional complexities, like interface with currently not implemented methods, code with some currently not required extension points, maybe a factory which is currently not required, and writing needless polymorphic code thinking about future extensibility. So, to summarize this, adding not needed extension points which is not required yet is a bad practice which leads to needless complexity. Okay, note that there are more design smells, but for now, I guess this many is sufficient to move ahead. Now, if you see these design smells in your code, that means you have technical debt. And that's the time to correct your design using solid design principles. So, with this, I hope we have built enough motivation to learn these design principles. See you in next part with single responsibility principle. If you like the video, don't forget to subscribe the channel and drop in your comments for all the future videos on C Sharp and other technologies. Thanks for watching.